Trigonometric equations. Objectives. Solve equations involving a single trigonometric function. Solve trigonometric equations using a calculator. Solve trigonometric equations that involve factoring. Solve trigonometric equations using fundamental identities. And solve trigonometric equations with multiple angles. Solving trigonometric equations in sine and cosine. The period of both the sine function and the cosine function is 2 pi. In other words, in every 2 pi units, the y values repeat. If we need to find all possible solutions, then we must add 2 pi k, where k is an integer, to the initial solution. For tangent, we would add pi k, since the period of the tangent function is pi. Here, let's find all possible exact radian solutions for the equation 2 sine t plus 1 equals 0. So first, we'll want to solve for sine t. 2 sine t is equal to -1. Sine t is equal to a -1/2. Now, thinking about on the unit circle where the sine of t is equal to a -1/2, we're going to have t equals 7 pi over 6 and t equals 11 pi over 6. Now, to make sure that we are capturing all solutions that are coterminal with that 7 pi over 6 as we go around the unit circle in either direction, what we'll do is say plus 2 pi k. Same with the 11 pi over 6. We're going to add 2 pi k, and then we'll say as k is an element of the integers. So if k were 0, this whole term would go away and we'd have 7 pi over 6. If we had k is 1, then 2 pi would be added to the 7 pi over 6. If k were 2, then 4 pi, or 2 more positive rotations, will be added to 7 pi over 6. We also have k equaling -1, -2, -3, and so on. As long as k is an integer, these two formulas will help you to capture all of the solutions that could ever occur. Find all possible radian solutions for the equation approximating to 2 decimal places. Here I have 5 cosine theta minus 1 is 0.8. Our first job is to go ahead and solve for cosine theta. So 5 cosine theta is equal to 1.8. When I divide both sides by 5, I have cosine theta equals 0.36. Now, this is not one of our special values, so we'll want to make sure that we grab our calculator. In radian mode, we'll go into the trig menu and use the inverse cosine, entering 0.36, and we have about 1.20 radians. Okay, so theta is approximately equal to 1.20 radians. To make sure that we capture all possible radian solutions that are coterminal with that, we'll add 2 pi k. But remember, we're talking about on the unit circle, 1.2 radians is somewhere in this first quadrant here. The other place where the cosine of theta is 0.36 would be in quadrant 4. So we'll take this 2 pi radians and subtract off the 1.2 radians. So I'm going to have in the calculator 2 pi and subtract off the 1.20 radians. So we have about 5.08 radians. So theta is approximately 5.08, and capturing all possible solutions, we add 2 pi k, where k is an element of the integers. Solve in exact radians. Square root of 3 cosecant theta equals -2. We'll find all solutions from 0 to 2 pi. So first let's go ahead and solve for cosecant theta. Cosecant of theta is -2 over the square root of 3. Now I know the cosecant of theta is the same as 1 over sine theta. So let's go ahead and use that identity to change this to being in terms of sine instead of cosecant theta. Now I can go ahead and solve for sine theta. Let's go ahead and just cross multiply. I have a -2 sine of theta is equal to the square root of 3. That's 1 times square root of 3. And then solve for sine theta. Sine theta is equal to negative square root of 3 over 2. Now we have to try and include all of the solutions within 0 to 2 pi, where the sine of theta is negative square root of 3 over 2. That's going to be at a theta of 4 pi over 3, or 5 pi over 3. Solve in exact radians. The tangent of theta minus pi over 2 equals square root 3. So this is already solved for tangent of some angle, so I need to go ahead and write what that angle is. It's theta minus pi over 2. And where is the tangent of some angle, the square root of 3? That's going to be at pi over 3, or that angle could be equal to 4 pi over 3. Now we can solve for theta. So I'll add pi over 2 to both sides of both of those equations. This gives me a theta of 5 pi over 6. This one gives me a theta of 11 pi over 6. So theta equals 5 pi over 6, or 11 pi over 6. Solve in exact radians. Here I have 2 times the tangent of x plus 3 equals 5 plus tangent of x. So the first thing I'll need to do is get my tangent of x all on one side. Let's go ahead and distribute this 2 to both of those terms. That will be 2 tangent of x plus 6 equals 5 plus tangent x. Subtracting tangent x from both sides, that'll give me a tangent x on the left side, and subtracting 6 from both sides, that will give me a -1 on the right hand side. So where is the tangent of some angle -1 between 0 and 2 pi? That would be an x of 3 pi over 4, or an x of 7 pi over 4. Solve in degrees rounded to 1 decimal place. Here I have 16 sine t cosine t equals 6 sine t. So think about this as being an equation like 16 a b equals 6a. If we were to try and solve this, we will want to get both terms on the left-hand side and equal to 0 so that we could factor out the greatest common factor. That greatest common factor would be 2a, and we'd be left with 8b minus 3 equals 0. So we'll do similarly on this problem. I'm going to have 16 sine t cosine t minus 6 sine t equals 0. Now my greatest common factor is going to be 2 sine t, and I'm left with 8 cosine t minus 3 equals 0. So now 2 sine t equals 0 and 8 cosine t minus 3 equals 0. So here the sine of t equals 0, and here the cosine of t is equal to 3/8. So where is the sine of t 0 between 0 and 360 degrees? That's going to be a t of 0 degrees or a t of 180 degrees. Then where is the cosine of t equal to 3/8? Well, that's not one of our special values, so we're going to use our calculator and the inverse function to calculate. Making sure that we're in degree mode, we're going to go into the trig menu and pick up the inverse cosine function, entering 3/8, and we get about 67.9, that's going to round up to 68.0 degrees. So t would be approximately 68.0 degrees. Now remembering that we're on the unit circle here at 68 degrees, the cosine is also 3/8 somewhere over here. So to get to that, we're going to take 360 degrees and subtract off the 68.0 degrees. So 360 and subtract off that angle, and we get about 292.0 degrees. So 292.0 degrees for our other approximate angle. And that will be all of the solutions within 0 to 360 degrees. 2 of them are exact and 2 of them are rounded off. At times, we can use an identity to convert to like trigonometric functions. Solve in exact radians. 2 sine squared theta minus cosine theta minus 1 equals 0. I'm going to use the Pythagorean identity to change sine squared theta into terms of cosine. So this will be 2 times sine squared theta is 1 minus cosine squared theta minus cosine theta minus 1 equals 0. Now this is similar to algebraically if we had an equation like 2 times 1 minus m squared minus m minus 1 equals 0. To be able to solve that, we need to get this all distributed, collect like terms, get things in descending order, and try to factor in order to solve, because this is a quadratic. So this is a quadratic trigonometric equation. We do the same steps just using those trig functions. So this will be 2 minus 2 cosine squared theta minus cosine theta minus 1 equals 0. So this is a negative 2 cosine squared theta minus cosine theta plus 1 equals 0. Now if you're like me, you don't like the leading coefficient on these to be negative, so I'd like to go ahead and either multiply through by a negative 1 on both sides or divide both sides by negative 1. Either way, that will give me a 2 cosine squared theta plus cosine theta minus 1 equals 0. And now we try to factor. So I know that my 2 cosine squared theta has to come from 2 cosine theta times cosine theta. And I know I'm going to have different signs. I'm going to have ones here. If I could make this a positive 2 cosine theta and this a negative cosine theta, that's going to give me my cosine theta that I need in the middle. So solving both of those, I now have cosine theta equals 1/2 and cosine theta equals a negative 1. So where is the cosine of theta a positive half? That's going to be a theta of pi over 3 or 5 pi over 3. And where is the cosine of theta negative 1? That's going to be at pi. So I have 3 solutions for this particular trig equation. Solve in radians rounded to 2 decimal places. 8 sine squared x minus 2 sine x equals 0. So trying to solve this, I'm going to have to factor again. 4 sine x plus 1 and 2 sine x minus 1 equals 0 will be the way that factors. With multiple angles, you'll modify your technique in order to capture your solutions. Let's solve cosine of 2x equals 1/2. Well, we've already solved for cosine of the angle, so where would the cosine of that angle equal 1/2? That's going to be at pi over 3. Or we could also have at 5 pi over 3. Now this is where we have to modify a little bit. I'm going to go ahead and capture all solutions by adding 2 pi k at this step. The reason being that this is not just an x equals, it's a 2x equals. And so when I have to divide both sides by 2 or multiply both sides by 1/2, then it affects not only that original angle, but it's going to affect this plus 2 pi k, and we'll be able to catch all the solutions in 0 to 2 pi that actually work for this. So I'm going to multiply both sides by 1/2 to get my x by itself. It's going to be a pi over 6 plus pi k. The other will be x equals 5 pi over 6 plus pi k. Again, just multiplying both sides through by 1/2. Now, we don't care about getting all the solutions ever that could occur. We want to know what all the solutions are in 0 to 2 pi. So this is where using the formula that we came up with is going to work. Starting with a k of 0, I get an x of pi over 6. Now if k is 1, then I'm adding pi to pi over 6, and that gets me a 7 pi over 6. If I make k 2, then I'm adding 2 pi to pi over 6, and that's going to get me over the 2 pi amount. So I've exhausted that formula. I've gotten all the angles out of it that I can. The other, I get 5 pi over 6 if k were to be 0. If k were 1, then I'd be adding pi to 5 pi over 6, and I would get 11 pi over 6. If I add yet another pi, letting k equal 2, then I'd be adding 2 pi to 5 pi over 6, and that's definitely too big. It goes past the 2 pi. So I have 4 solutions in the interval 0 to 2 pi for this equation. Solve cosecant of 3x equals -2. This is another multiple angle. So we also have this cosecant. We need to change it to be in terms of sine. So cosecant of 3x is the same as 1 over the sine of 3x. That equals -2. Now, if I would multiply both sides by sine of 3x, I would have -2 sine 3x equals 1. And then dividing both sides by -2, I have sine of 3x equals a -1/2. So here we are again with the need to make a formula to capture all of our solutions because we have multiple angles here. So the sine of this angle is -1/2, and where would that occur? That's going to happen at 7 pi over 6, or it can happen at 11 pi over 6. And remember, we're adding 2 pi k to both of those at this step of the process so that we can catch all of the solutions. I'm going to multiply through by 1/3 on both sides of both of these equations, and that'll get me x equals 7 pi over 18 plus 2 pi over 3k, or x equals 11 pi over 18 plus 2 pi over 3k. Now I can go ahead and use the formula that I've come up with here to get all my solutions that lie between 0 and 2 pi. So x is going to be equal to 7 pi over 18. That happens when k is 0. Now, if k is 1, then I'll be adding 2 pi over 3, or 12 pi over 18 to the 7 pi over 18, and that will make 19 pi over 18. If k is 2, then I'm going to be adding 4 pi over 3 to 7 pi over 18. That's going to give me 31 pi over 18. Now if I add another 2 pi over 3, then I would be adding 2 pi total to the 7 pi over 18, and that's definitely over the 2 pi that I need to find answers in. So I go to my next formula. Since I've exhausted that first formula, I have 11 pi over 18 when k is 0. If k were 1, I'd be adding 2 pi over 3 to that, and that's going to give me 23 pi over 18. And adding another 2 pi over 3, I would get 35 pi over 18. And if I add another 2 pi over 3, it will be past my 2 pi. So I've exhausted that formula as well. And these are all of the solutions between 0 and 2 pi. Now I want to show you how to make this a little bit easier by using the calculator. Remember, these are all fractions of pi that we're adding, so we can just deal with the fraction part on the calculator. We've got 7 over 18. That was our first angle, so 7 over 18 pi, or 7 pi over 18. And then I can add 2/3. We know that's 2/3 of a pi, but I'm just dealing with the fractions here. So adding 2/3, and make sure that you convert that decimal to fraction. There's your 19 pi over 18. And then we can enter that again, and there's the 31 pi over 18. Now if I do it one more time, I'm adding another 2 pi over 3 this way. I'm definitely over 2 pi. So you can see that we've exhausted that formula using it 3 times, and it's done. Then I have my 11/18 pi. Just go ahead and hit enter. Remember, we're not going to use the pi, we're just talking about the fraction part of this. And I'm adding 2/3. Remember to convert that to a fraction. And there's your next angle of 23 pi over 18. Run it again. There's 35 pi over 18. And just to show you, if we use the formula one more time, it's definitely past the 2 pi boundary. So we've exhausted that formula. It's a really nice way to do it on the calculator to get those fractions of pi for your radian measures. Solve. Use an identity in order to make like angles. Like angles, because here I have 2 beta and here it's just a single beta. So I'm going to use the double angle identity for sine. This would be the 3 that's out front times 2 sine beta times cosine beta plus my 5 sine beta equals 0. Now this is 6 sine beta cosine beta plus 5 sine beta equals 0. So now what I want to do is factor out a sine beta. So how do you know? This is similar to if we had 6xy plus 5x equals 0. What would we do to solve that? We would factor out the x, and we would be left with 6y plus 5 equals 0. So we're doing a very similar process, looking at this term and saying, well, the sine beta is our greatest common factor. Let's take that out. And then I'm left with 6 cosine beta plus 5 equals 0. Then I go ahead and solve. Sine of beta equals 0, or cosine beta is a negative 5, 6. So where is the sine of beta equal to 0? That's going to be at 0 radians or pi radians. So beta is equal to 0 or pi. And here, cosine beta is negative 5, 6. That's not one of our special angles, so we'll need to use our calculator. Making sure that we're in radian mode, I go into the trig menu and pick up the inverse cosine function of negative 5, 6, and I get about 2.56 radians. So beta is approximately 2.56 radians. But remember, we're talking about the unit circle here, and we're here somewhere in this quadrant. So where else is the cosine of beta negative 5, 6? It's going to be somewhere in here. So if we're at some 2.56 radians here, so to get that angle in the third quadrant, we'll take 2 pi and subtract off the 2.56 radians. So 2 pi minus the 2.56 radians, and that gives me 3.73 radians. So there are my 4 solutions, 2 of them exact and 2 of them approximate.